Hello. So I'm not feeling that great, which is actually kind of a lie. I'm feeling pretty much awful. I got real sick over the snow day and was so sick I couldn't even make the video that I wanted to send you yesterday. So I'm going to make it now for you today. So we're going to basically shift everything back one day. I apologize in advance, both for any confusion that created and also for the somewhat lower production quality of this video. But it is what it will be. We're going to get you through this, get you started the homework, and get you out of here for fresh and retreat. So I want to look at this stuff called redox reactions. I want to go through a few slides here on the left on the Google Slides and then go through here and kind of fill out the notes with you and let you get started on your homework properly. So kind of flip back and forth here and hopefully get you out of here. So we're going to be looking at redox reactions, which are just another way of understanding the synthesis, combustion, decomp, replacement, single and double, of course, that we've been talking about. Those kinds of reactions are all real, but all of them could be explained a different way, which is something called redox, which is the chemist's shorthand for saying oxidation reduction. Oxidation reduction understands chemistry in the transfer of electrons. It says the reaction only happens because we're moving electrons around, which I think most of us are pretty clear on. Like, oh yeah, there's these valence and they change. And oxidation reduction is really just going into this a little bit more in depth and saying, okay, well, what's actually causing those electrons to move, and can I predict if the reaction is going to happen based on that? We're really just interested in the idea. Redox gets really complicated really fast, especially balancing it, so we're not going to do that. We're just going to talk about redoxes in general. Perhaps you remember burning the magnesium ribbon a while ago, really bright white light, and of course I think at the top the reaction here, oh good, it's a combustion, it's a synthesis, but it's also a redox. It turns out that the magnesium is going to lose 2 electrons, and each of those electrons are going to be given to the oxygen, which is kind of logical. I mean, Mg is a +2 charge, O is a 2- charge. I don't see anything new here from, let's say, October, when we first learned what an ion is. And for a lot of reactions, it really is as easy as just using the ion's charge. But it's not always that easy. And so there's some really long list of rules here. And, you know, these rules, yeah, this is all the possible ones. But I think it's easier to look at these rules in the way I told you at the bottom. Okay, just make them as simple as possible. Okay, so an element by itself is 0. I don't care if it's diatomic. I don't care if it's bound to itself 8 times. The element, if it's just one capital letter in the compound, well, that's going to be equal to 0, which I think makes good sense. I mean, we don't write like Na plus in the middle of a challenge. Except we do sometimes. In redox, it can be useful to put Na plus into an equation, excuse me. So if I write that, there's a reason for me writing it, and the charge is equal to the charge. Now, I think these two rules together make sense. If the element's alone, it's 0, unless there's a charge on it already given to you, in which case, well, just trust the charge. And this is true not only for elements by themselves, but for compounds. If something like iron oxide here doesn't have a charge, it's 0. This nitrogen triiodide is 0 because it doesn't have a charge. But this nitrate ion with its little tiny minus here, that's a -1 because, well, I told you it's -1. Just like ammonium is going to be a +1 because I told you it's a +1. Or phosphate's a -3 because I told you it's a -3. So just trust what's going on here for a moment. You have a couple friends that are useful to you. When you're working these problems, you almost always want to see if you have oxygen, because oxygen is very well behaved when it comes to redox. You know, with one exception, oxygen is always -2, which in this class is going to be always the case. Oxygen is -2. So if we come into an oxygen, I know it's -2, and hydrogen's +1. Really, that's going to be the case any time in this class. And so oxygen and hydrogen can be keys mixed in with the stuff about, well, charge and isolation being 0, and that's pretty great. Occasionally that's not enough and you need to use an ion sheet, although frankly in this class, if you know oxygen is -2, hydrogen's +1, and things are equal to 0 or their charge, you're pretty much good. And I gave you these rules for determining on the back of your notes today if you need them. Okay, let's come over here. So these are kind of made up things. I mean, okay, oxygen is a -2 and hydrogen's a +1. It sounds like they're charged, but really, these aren't exactly their charge. It's actually how oxidized or reduced they are. So for instance, in the reaction between potassium and chlorine, well, potassium here is a 0 because it's alone, and chlorine's a 0 because it's alone. So neither of these have oxidation or reduction, right? This is 0, this is 0. Makes good sense to me because they're alone and they don't have a charge. However, when I come over here, K and Cl are bonded together now, and K is always a +1, which means Cl has to be a minus in this case. So all of a sudden, my oxidation numbers have changed as a result of this arrow, right? I went from 0 to +1. I went from 0 to -1. Because the oxidation numbers changed, we say that we had a reaction. It's really that straightforward. I'm not asked you to write this down. I'm just going to try to show you what's going on here. So, what are the oxidation states in sodium nitrate? Okay, so sodium is always a +1. Sorry about that. Oh, this is a good one. Sodium is always a +1. And oxygen is always a -2. So I would have sodium +1, oxygen -2, but I have 3 oxygens. So -2 times 6, or -2 times 3 is 6, excuse me. And I got a +1 here, which means the nitrogen actually is in a +5 state, which is weird because if you maybe remember from chemistry, nitrogen is generally a -3. Okay, that doesn't make a lot of sense, Mr. Rendick, but what I'm trying to show you is basically we're going to work backwards. I know what oxygen is, I know what sodium is, so I've got to figure out what N is to make something true, which is this whole thing needs to be, well, equal to 0. Right? If this isn't equal to 0, then I violate the charge here. So let's take a look at some of the stuff in your notes here. So I've got the chemical potassium chlorate, great oxidizer. And I want to know the oxidation state of the chlorine. Okay, so I'm going to work through this part first. Let's see, I know something about oxygen. Oxygen is always equal to -2, right? And I have 3. So oxygen total equals -6. I think that makes sense. And I know something about potassium. Potassium is always +1. Okay. Oopsies. I don't like word. Definition of insanity. All right, there we go. Close enough for the girls I go out with. K is always equal to +1, and I have 1. So the total potassium is going to be equal to +1. All right, so I've got a -6 and a +1, and this whole thing is equal to 0 because, well, there's no charge given. So really, I need to come up with Cl, right? Cl is, let's call it X, and, well, 1 plus X minus 6 equals 0, so X has to be what? +5. And you don't have to write out all your work this way. I'm trying to communicate as best as I can right now, and it's, well, 5 in the morning and I don't feel great. So in this case, chlorine's +5, but if you're playing along, you're like, well, what the heck, Mr. Nick? Chlorine's a -1. It's a halogen. It's always going to want to gain 1 electron. And that's kind of true, but in this case, it wants to lose 5 electrons to make KClO3. And so this is weird. I can't just trust my ion sheet. All right, so let's look at this next one too. Oh, that's annoying. We'll find the oxidation state of the nitrate ion here. Okay, so I always start with the same thing. My total is -1. Because I've got a charge here that I've given you, I know that I'm trying to find a -1 total. So up here it was 0 because there's no charge given. But down here, it's a -1 because, well, nitrate's a -1 ion, and I've told you that. Because if my total is -1, I got to come up with a way that N plus the oxygens equals -1. Put another way, like nitrogen plus oxygen equals -1, right? So let's see, nitrogen in this case. Well, I don't know anything about that. I know about oxygen, right? And oxygen is always -2. And you can see how oxygen is going to be your friend here. Oxygen is always -2. And I have 3 again. So O total is equal to -6. So effectively, I have X for nitrogen. And my -6 from oxygen equals -1. And it turns out, again, it's +5, right? 5 plus -6 is -1. Which is kind of neat. Okay. I'm asking you to do 20 of these on your homework. And they're honestly not too bad. And I'll try to do the homework and put a key up on it here in a bit, but not this second. All right, so let's look at one more example here, which is oxygen. Oxygen is always -2, right? But it turns out that's not exactly true, because when things are alone, the total is equal to 0, right? Like this doesn't have a charge. This doesn't have anything out front. So this has to be equal to 0 as a group. So each of the individual oxygens inside this has to also be 0. It's not like I got a -1 and a +1 or a -2 and a +2, right? The charge of this whole group is 0. So, well, the total here is 0, so the individual parts are 0. Okay, so we're there. Hopefully that makes some sense. And well, where we're going here, I'm going to just make a couple definitions before you leave, is understanding why these changes are happening. Why am I allowed to get N+5 or Cl+5, or why in certain circumstances do I get numbers that don't make sense to the ion sheet? And that's because I've got oxidation and reduction. And so oxidation is, as it says there on the left, the complete or partial loss, oh my god, of electrons. And it turns out oxidation and reduction are partnered processes. So if I have oxidation, I have to have reduction, which is the complete or partial gain of electrons. All right, so I've got those two things. And those two things are partnered processes, because if they're not, your reaction would look something like this, right? That lightning isn't balanced. The transfer of electrons is quite, well, negative in this case. And you get lightning, you get electricity. And these reactions work with electricity, but in our lab, if we were to try to have a reaction like this, obviously I'm going to blow my lab up. So we're always going to have oxidation and reduction, well, picking things from one to the other. And a lot of students struggle with remembering which one's loss and which one's gain. And so the two ways that I've worked on to know these are two little like mnemonics, two little memorizing. Personally, me, I use oil rig. So oil rig, oxidation is loss, reduction is gain. And so for me, that works. I just remember the word oil rig and I remember what the thing is. In vogue right now in chemistry education is Leo goes grr, because it also talks about the fact there are electrons. So Leo goes grr, losing electrons oxidizes, while gaining electrons reduces. Fine, whatever you want to do to memorize these works, as long as you know that oxidation is the partial loss and reduction is the partial gain. Right? And where we're going to go, and what we're going to look at together on Monday, is understanding when things are oxidized or reduced. Okay, so if something is reduced, it actually means the oxidation number goes down. And if it's oxidized, the number goes up. Not too bad, right? Because if I lose electrons, I get more positive. If I gain electrons, reduction is gain. I gain more negatives. So if a number is reduced, and if it's oxidized, it rises. All right, now that's really all I'm asking you to do. I think there's enough there. You got the homework from the stuff I gave you on Tuesday. There's 20 problems. Please give it a try doing this process up top. And again, thank you for bearing with me in terms of this video. I know it's not the easiest way to do things. It's just the only way you actually can do them today. I hope you have a good weekend, and if you're part of the grounds crew, I hope you enjoy that experience, and if not, enjoy a little bit more restful day. Have a good one.